Welcome to Kanerika's podcast, The Digital Shift. You know, it is fascinating how the most expensive problems in the business world are often the quietest ones.
Right. They really are.
Yeah, they do not announce themselves with a sudden catastrophic explosion on the factory floor. Instead, they just quietly drain resources, minute by minute, until something finally snaps. Today, we're looking at a problem that costs U.S. manufacturers an estimated $15 billion a year.
And that is 50 billion with a B, right?
Exactly, 50 billion. And this comes entirely from unplanned downtime. When you break that number down into physical reality, it equates to about 800 hours of lost production per plant annually.
Wow.
I mean, that is more than 15 hours of lost time every single week where machines sit idle, workers are waiting, and capital is just bleeding out.
And we have to remember that is just the average. If you are managing operations in high-stakes environments like pharmaceuticals or petrochemicals, the financial bleed is exponential.
I can only imagine.
Yeah, a single incident of unplanned downtime can cost a facility up to $1.7 million per hour. When you are operating at that scale, every passing minute is a massive hit to the bottom line, not to mention the downstream supply chain chaos it creates.
That is exactly why our mission for this deep dive is to explore how AI-powered digital twins are solving this multi-billion-dollar problem.
Yeah.
We are going to unpack how businesses are shifting away from merely reacting to crises and moving toward predicting and acting on them long before they happen.
It is such an important shift.
It really is. If you are listening to this and you manage physical assets, you know that the goal is not just to fix things faster.
Right.
It is to prevent them from ever breaking in the first place.
It truly is a fundamental shift in how we manage industrial operations. But to understand the solution, we first have to understand why this problem still exists in an era where we have sensors on absolutely everything.
Right. We have so much data now.
Exactly. Industrial equipment rarely fails without giving us a warning. A massive industrial pump will start vibrating just a few millimeters differently for weeks before it actually seizes.
It gives you a sign.
It always gives a sign. A cooling tower's temperature will drift by a fraction of a degree long before the internal components foul. The energy draw creeps upward. You know, these warning signs are not invisible. They are highly measurable, and they are constantly broadcasting their status.
Which raises an incredibly obvious and, frankly, frustrating question. If organizations are already collecting terabytes of data from their operations every single day, why do these critical machines still break by surprise?
Because the data is unread. And more importantly, it is completely disconnected. The information is locked inside isolated silos that were never designed to speak to one another.
So they just sit there in a vacuum.
Precisely. On the factory floor, you have your SCADA systems. Those are handling the live, real-time sensor data. But that telemetry is usually locked inside a legacy historian database that only a handful of engineers can access or decipher. Then, in a completely separate department, you have your computerized maintenance management systems, which hold the historical records of what broke and when it was repaired.
And I imagine the finance and inventory teams have their own completely separate ecosystem as well.
You nailed it. Entirely disconnected from the operational and maintenance data, you have enterprise resource planning systems tracking replacement parts, supply chain costs, and inventory levels.
Wow, so nothing talks to anything else.
Exactly. And finally, perhaps the most critical silo of all, you have tribal knowledge. That is the operational intuition that lives entirely inside a senior supervisor's head. You know, the person who knows that a specific machine always runs hot in July.
Oh, that makes so much sense.
Yeah, because this data never meets in one place. Over 80% of manufacturers cannot even calculate their true downtime costs.
Let me introduce an analogy here to make this concrete for anyone trying to visualize the problem. Having all these disconnected systems is like having all the pieces of a complex jigsaw puzzle scattered across different rooms of your house.
That is a great way to look at it.
Yeah, you technically possess the entire picture.
Yeah.
You own all the data. But you cannot actually see what the picture is until you gather all the pieces on one central table. And usually by the time you manage to manually pull the SCADA data, check the maintenance logs, and verify the inventory, the machine is already broken.
That is a highly accurate way to frame it. You simply do not have the connected visibility to answer the basic question of what will fail next.
So how do companies usually handle this?
Well, this brings us to the concept of the maintenance maturity curve, which categorizes how organizations handle their assets. Most companies start at the reactive stage.
Which means exactly what it sounds like.
Right. This means running equipment until it literally breaks and then rushing to fix it. It is the cheapest system to set up, but by far the most expensive to run because you are paying for emergency replacement parts, overtime labor, and taking the full hit of halted production.
But even the step up from that, which is preventive maintenance, feels incredibly inefficient to me.
Oh, it absolutely is.
Because that is where you service equipment on a fixed calendar schedule, regardless of its actual condition, right?
Exactly.
So you are swapping out a perfectly good fan bearing every 6 months just because the manufacturer's manual told you to.
Yeah.
That feels like a massive waste of capital, just throwing away healthy parts to avoid a potential failure.
It is a massive waste. Preventive maintenance is essentially an educated guess. It treats every machine exactly the same, ignoring the unique environmental stresses each one faces.
Right.
That is why the true return on investment begins at the third stage, which is predictive maintenance. Instead of a calendar, you act based on what the asset's real condition data is telling you right now.
I want to push back on this progression, though. Predictive maintenance has been a buzzword for a decade.
It definitely has.
Knowing a machine is going to break does not automatically mean you have the parts or the personnel ready to fix it. If the prediction just sits on a dashboard, it is basically useless.
You are hitting on the exact limitation of standard predictive models. And that is exactly why we are now entering the fourth stage of the maturity curve. We call this the agentic stage.
The agentic stage.
Yes. This is where artificial intelligence not only predicts a failure, but it prioritizes that failure against every other issue in your global portfolio. Then it autonomously recommends and triggers the necessary action to fix it.
Oh, wow.
Yeah, it completely closes the loop between the prediction and the physical repair.
So to move from a fixed calendar approach to this real-time agentic foresight, an organization needs a specific technological foundation. We are talking about the AI-powered digital twin.
Correct. But we need to define what a digital twin actually is in this context, because the term gets thrown around a lot by software vendors.
Yeah, it can mean a lot of things.
It really can. A digital twin is not just a fancy 3D dashboard with a nicer user interface. To be truly effective, it must be built on 4 distinct pillars.
Okay, let us go through them.
First, it requires continuous live synchronization. The virtual model must stay perfectly matched to the physical asset in real time, pulling in that live SCADA data rather than relying on batch updates from yesterday.
Meaning the twin is living and breathing alongside the actual machine on the factory floor.
Precisely. The second pillar involves learning a healthy baseline for that specific individual asset.
So it knows what normal looks like.
Exactly. The system uses machine learning to understand what normal behavior looks like for that exact machine across different production loads and weather conditions. It does not rely on a generic fixed threshold set by the manufacturer.
Right, because every machine is in a different environment.
Exactly. The third pillar is early drift detection. Because the AI knows the exact baseline, it can surface microscopic anomalies well before a traditional threshold alarm would ever trigger.
And the fourth pillar is where the agentic element comes in.
Right.
It actually recommends a specific action rather than just flashing a warning light.
Yes. The twin does not just say something is wrong. It suggests the exact maintenance step required to fix it, pulling from historical repair data to know what worked in the past.
That is incredible.
It really is. This concept actually traces its roots back to NASA during the Apollo missions. They built virtual replicas of spacecraft systems to diagnose problems mid-flight.
Oh, that makes perfect sense.
Yeah, they needed a way to troubleshoot oxygen tanks and power grids when they had absolutely zero physical access to the hardware. Industrial digital twins apply that exact same logic to a factory floor, a power grid, or a water treatment facility.
I think the difference between traditional monitoring and a digital twin is crucial here. Traditional monitoring feels a lot like the check engine light in your car.
Very much so.
By the time that light turns on, the engine is already running hot, the damage is actively happening, and you are already in trouble. The digital twin, conversely, is like having a master mechanic riding in your passenger seat.
I love that analogy.
Yeah, they turn to you and say, based on the current temperature, your driving habits over the last month, and the microscopic vibrations in the steering column, your serpentine belt is going to snap in exactly 4 days.
That is an excellent visualization. You are moving from knowing what is happening right now to knowing what is mathematically likely to happen next.
It changes everything.
It does. Let us take this from the abstract and bring it into a tangible, real-world scenario to see exactly how this works in practice. A great example to look at is a cooling tower.
Why a cooling tower specifically?
Because they are ubiquitous. They are used across nearly every heavy industry for heat rejection, from data centers to steel mills. Crucially, they fail gradually, emitting very clear warning signs through their vibration and temperature data.
This is a perfect scenario to explore then. Walk us through how an AI system actually manages something that complex.
Well, when we at Kanerika deploy these solutions for our clients, often partnering with Microsoft and Esri, we see the transformation happen in a very specific six-step sequence.
Okay, what is the first step?
It always starts with monitoring at scale. Imagine you are overseeing a global portfolio of 600 cooling towers spread across different continents.
Okay, wait. Let me legitimately challenge the feasibility of this. With 600 global assets, you are dealing with millions of data points a second.
Yes, you are.
How does the AI actually decide which cooling tower is a true emergency versus just a minor anomaly? If a tower in the Arizona desert is running hot in July, that is expected. If a tower in Iceland is running hot in December, that is a crisis. How does the system not just drown the maintenance manager in false positive alerts?
That is the most common concern, and it is exactly where the second step prioritization comes in. The AI does not just look at raw temperature.
What else is it looking at?
It filters down those hundreds of assets by combining the live telemetry with environmental context and location-based risk. The system inherently understands the ambient temperature differences between Arizona and Iceland because it is pulling in external weather data. Yeah, it synthesizes all these variables into a unified maintenance risk score. It filters out the noise of normal environmental stress. In our scenario, let us say a specific tower in a critical facility flags a risk score of 88 out of 100.
So the noise is completely filtered out, and we are looking directly at a highly critical, context-aware issue. What happens next?
We move to step 3, which is analyze and predict. The system drills into that specific cooling tower. It evaluates the CMMS maintenance history, the live SCADA telemetry, and the current operating conditions.
It looks at the whole picture.
Exactly. It notices that the cooling efficiency has dropped to 50% against a 90% target. It then identifies the likely root cause, which in this case is fan-bearing degradation.
So it spots the exact part.
Yes. And here is the crucial part. It provides an estimated remaining useful life for that specific component, let us say 12 days, and it attaches a confidence score to that prediction based on historical accuracy.
It gives you a highly specific time window to act, backed by probability.
Yes, it does. And that leads to the final steps, which are recommend and trigger. This is where the Agentic AI layer steps in.
Right, the autonomous part.
Exactly. A maintenance manager can use natural language to query the system, asking a simple question like, which assets are likely to fail in the next 30 days and halt production?
Just like talking to a person.
Exactly. The system not only provides the answer, but automatically initiates the solution. Using a tool like Microsoft Fabric Activator, it triggers an automated workflow.
What does that workflow look like?
It verifies that the replacement fan bearing is in the ERP inventory, it sends a work order to the CMMS, and it pushes a Microsoft Teams alert to dispatch a crew.
I have to stop you there and challenge the reality of this agentic phase.
Sure, go ahead.
Letting an AI automatically trigger work orders, allocate inventory, and dispatch human crews sounds like a massive liability. What happens if the AI hallucinates a fan-bearing failure or misinterprets a sensor glitch and dispatches a $5,000 emergency crew for absolutely no reason?
That is a critical point regarding AI safety and governance. We do not jump straight to fully autonomous actions. When we at Kanerika build these systems, we implement what we call a human-in-the-loop fallback.
Okay, how does that work?
The AI does all the heavy lifting. It drafts the work order, checks the inventory, and identifies the available technicians. But before any money is spent or any crew is deployed, a human manager gets a notification to review the AI's logic and simply click approve.
Ah, I see.
Yeah, as the model proves its accuracy over time, organizations can choose to automate the lower risk decisions, but the human always retains oversight on critical expenditures.
That makes a lot more sense. It acts as an incredibly efficient assistant rather than an uncontrolled autonomous agent.
Exactly.
But that brings us to a massive technical hurdle. A smart AI prediction is completely useless if your infrastructure cannot handle the underlying data.
This is very true.
If you are listening to this and managing a legacy facility right now, you are probably rolling your eyes at the idea of seamless AI integration when your SCADA system is running on a server from the late 90s.
That is a very common reality.
How do we avoid building yet another giant unmanageable data silo where we are just constantly copying and moving data around.
You are highlighting the core challenge of industrial digital transformation. Integrating decades-old legacy systems with modern cloud AI sounds like a nightmare because historically, it was.
Right, it was always a headache.
Yes. The traditional approach involved building complex extract, transform, and load pipelines, or ETLs, which constantly copy massive amounts of data from the source into a new cloud database.
Which must be incredibly slow.
It creates latency, it creates massive storage costs, and it breaks constantly. That brings us to the engine underneath this entire solution, which simplifies into 4 architectural stages: ingest, unify, predict, and act.
Let us unpack the ingest and unify stages, because that is where the bottleneck usually happens. How are modern systems avoiding the ETL pipeline nightmare?
This is where the technology stack becomes critical, specifically Microsoft Fabric, which acts as the unified data foundation.
Okay, how does Fabric do it differently?
Fabric utilizes a data lake architecture called OneLake. But instead of forcing you to copy your legacy SCADA data and your ERP data into OneLake, it uses features called shortcuts and mirroring.
Explain the mechanism behind that. How does a shortcut actually work to prevent data duplication?
Think of it like metadata indexing or API virtualization. Instead of duplicating terabytes of historical sensor data, Fabric leaves the data exactly where it lives, whether that is an on-premise SQL server, an AWS bucket, or a proprietary historian database.
So the data stays put.
Right. The shortcut just creates a lightweight, secure map to that data. When the AI model needs to run a prediction, it uses that map to query the exact bytes it needs in real time. It reads the data in place without ever moving it.
That is amazing.
It really is. It allows you to scale from thousands of sensor readings to billions on a single governed foundation without ballooning your storage costs.
That brilliantly solves the data volume and legacy integration problem. But earlier, when we discussed the cooling tower in Arizona, you mentioned the system understands ambient temperature and environmental context.
Yes, I did.
How does an AI model living in a corporate cloud know what the weather is doing at a specific physical facility?
That is where the partnership with Esri ArcGIS comes into the architecture. Esri provides the location intelligence engine. It enriches the AI predictions with crucial spatial and environmental context.
How does it get that context?
It uses a feature called the Living Atlas, which is essentially a massive real-time repository of global geographic and weather data.
So it is essentially giving the AI a weather radar. It is the difference between the AI knowing a pump is getting old and knowing a pump is getting old while a severe heat wave is actively driving up the ambient temperature of the facility.
That is the perfect metaphor. The AI uses that weather radar to understand external stressors. Environmental conditions directly influence how fast an industrial asset degrades.
That makes total sense.
Yeah, if humidity spikes, certain belts degrade faster. If temperatures drop below freezing, fluid dynamics change. The system pulls that real-time weather data through Esri, feeds it directly into the AI prediction model, and dynamically adjusts the remaining useful life estimate.
And I imagine that location intelligence is also critical for the final phase, when we actually have to send a human being to fix the problem.
Absolutely. Esri's spatial analysis powers that final act stage. When Microsoft Fabric Activator generates the work order, the system uses geographic routing to locate the nearest available technician with the right skill set.
Well, that is incredibly efficient.
It is. It factors in the current traffic or facility layout and routes them to the exact physical location of the asset, all within one automated workflow.
When we look at the bigger picture here, the implications extend far beyond cooling towers. We are talking about fundamentally changing how we maintain the physical infrastructure of the modern world. Let us talk about scale and industry impact.
The broader implication is that while the physical asset changes from industry to industry, the sequence of monitor, prioritize, predict, and act remains exactly the same.
It is a universal framework.
Exactly. Think about healthcare. We can apply this architecture to MRI machines. Instead of a hospital facing unexpected downtime and canceling dozens of critical patient scans, the digital twin detects a degrading cooling magnet and schedules proactive maintenance during the night shift.
The stakes there are literally life and death, not just financial.
Exactly. It applies to aviation, processing continuous telemetry from jet engine components to ensure maintenance happens before a plane is ever grounded.
Which is huge for safety.
Absolutely. It is critical for data centers, where a failure in the cooling infrastructure can take down cloud services for millions of users. And it is being aggressively adopted by utilities to monitor power grid transformers, which exhibit the exact same measurable degradation patterns before they blow out and cause a blackout.
And the market data reflects this massive shift in strategy. The global digital twin market is projected to grow roughly sevenfold by the year 2033. Predictive maintenance is the single largest application segment driving that growth.
It is growing incredibly fast.
And the financial returns validate the investment. Power generation facilities are seeing $5 to $12 back for every single dollar invested in these agentic programs. Steel plants, which operate in some of the harshest environments imaginable, are cutting their unplanned downtime by 30 to 50%.
Those numbers are incredibly compelling, but they come with an ultimate truth that every operational leader must understand.
What is that?
The core lesson here is that value only materializes when a prediction turns into a completed physical action. A highly accurate, AI-powered digital twin is completely worthless if it is just another complex dashboard that nobody opens because they're suffering from alert fatigue.
It is the difference between a system accurately predicting you're going to drive your car off a cliff and a system that actually reaches over and turns the steering wheel for you.
Precisely. The technology only pays for itself when the automated work order is generated, the technician is successfully dispatched, and the physical part is replaced before the machine fails. The entire architecture must be designed around driving that final action.
That transition from reactive chaos to agentic maintenance, where the system orchestrates that completed action, is exactly what we at Kanerika help enterprises achieve. We help operational teams assess their true AI maturity, build these connected data foundations without ripping out their legacy systems, and ensure that those AI predictions actually translate into automated, human-approved workflows.
It requires a very strategic alignment of legacy data structures, modern AI capabilities, and established business processes to successfully reach that fourth stage of maturity. You have to bridge the gap between the data scientists in the cloud and the mechanics on the factory floor.
Which leaves us with a fascinating and slightly philosophical dynamic to consider. As digital twins become more sophisticated and fully agentic, meaning they are accurately predicting failures, navigating the supply chain to buy replacement parts, and dispatching technicians with minimal human intervention, what happens to the traditional role of a maintenance manager?
That is a great question.
Are they still managing the physical machines, or are they now primarily managing and auditing the AI's decisions? It is a profound shift in human labor and expertise, and definitely something for you to mull over as we wrap up today's deep dive. Thank you for joining The Digital Shift.